Okay. So today what I'm going to do is finish our discussion of the standard model. In particular, I'm going to focus on the quark sector. Actually, one announcement maybe before I continue. So this is the last lecture. You are going to get one more problem set, the final problem set. It's just a normal problem set. Okay. It's not graded any differently. It's not any longer, not any more difficult, I think. I haven't quite finished writing it, so I'll send it out by email tonight, hopefully. And that'll be due, I guess, next Friday, as usual. But all of the usual problem set policies will apply to this problem set as well. Such as they are. I don't actually know what policies apply. Okay, good. Okay, let me remind you of where we left off last time. So the standard model is a gauge theory with a gauge group that is SU3 times SU2 times U1. The important thing that one needs to keep in mind is that the U1 here is not electromagnetism, but rather a different U1 called hypercharge. The idea being that there is a Higgs field, which is a complex scalar field, or rather a pair of complex scalar fields that transform in some non-trivial way under the SU2 times SU21 gauge transformations. So in particular, it's a singlet under SU3, a doublet under SU2, and has charge minus 1/2 under the U1 hypercharge. And this Higgs field acquires a vacuum expectation value, which by convention we usually put in the upper component of the two-component column vector. We hear this is the two-component vector that describes the SU2 gauge transformation property. And in fact, you can think of SU2 times U1 just as U2, the set of unitary 2x2 matrices. And if you think about it for a second, you can fairly easily see that having a complex doublet with a non-trivial vacuum expectation value leaves only a U1 sitting inside SU2 times U1 unbroken. Now, the easiest way to think of this is to think of the SU2 times U1 gauge transformations as generated by 2x2 unitary matrices. And if you think about what 2x2 matrix acting on this two-component vector V0, it leaves that vector invariant. Well, it's going to be the 2x2 matrix 1, 0, 0, 0. Okay. So the 2x2 unitary matrices generated by that will leave this vector invariant. And so the gauge theory, the component of the SU2 times U1 gauge fields pointing in this direction here will be massless, and that will be the photon. And the other three gauge fields, typically referred to as the Z boson and a pair of WZ bosons, become massive. And their mass depends on the value of that parameter V, the Higgs valve. So usually what we do is we write the gauge field A mu. So what is the gauge field A mu? It's a linear combination of A3, which is the component of the SU2 gauge field that points in the sigma 3 direction, and the U1 hypercharge, whose gauge field is typically denoted B. And if you think about the U1 hypercharge as sitting inside U2, it's the thing proportional to the identity matrix. And so, sigma 3 is proportional to 1 minus 1, and the identity matrix is proportional to 1, 1. And so, since the gauge field that is unbroken is the one proportional to this matrix here. It's just a linear combination of A3 and the U1 hypercharge. Okay, and that's what this linear combination is here. The presence of those angles, sine theta weak and cosine theta weak, come from the fact that the gauge couplings for the SU2 and U1 are not the same. So remember that theta weak was defined in terms of the ratio G1 over G2. So we just need to take that into account. Good. Now, in addition to the gauge theory, we have 3 generations, which is a fancy way of saying 3 copies of the following matter fields. So we have leptons, which we discussed yesterday and we'll return to a little bit today, which are defined by the feature that they don't carry color charge. And there are 2 different kinds of leptons. So there's a lepton doublet, usually denoted L. And if we think of it as a two-component field, writing out the SU2 index explicitly, its upper component is the neutrino field, the lower component is the left-handed electron field. And then, sorry, I guess I should write that as 1, 1, 1. Okay. We have the other component of the electron field, the positron field, E bar, where I remind you that, as I emphasized last time, bar here just is part of the name of the field. Okay, it's a slightly confusing notation. But these are left-handed vial spinners. And because the the matter fields are chiral, that is to say they're not invariant under parity transformations, we have a left-handed sector and a right-handed sector that are not identical, the gauge theory is going to be chiral. So the SU2 gauge theory is going to be chiral. And so you do have to worry about chiral anomalies, as you learned in the lecture on chiral anomalies. And it is a straightforward exercise, but not one that we're going to go through in this class, to check that indeed the SU2 gauge theory is not anomalous. Okay, the anomaly depends on how many matter fields you have, transforming in what sorts of representations. You go ahead and add it all up for the standard model. The SU2 weak force is indeed not anomalous. Okay? And that is an important constraint on the various charges of the fields in the standard model. Okay? So in one of the ways that people try and explain why the standard model has fields with the sort of charge assignments that they do, anomaly cancellation is one of the standard things that people use. In fact, one can also think about gravitational anomalies. This is not something that we've considered in this course. But because these are left-handed vial spinners, they are chiral. Well, they also transform non-trivially under coordinate transformations, which are the analog of gauge transformations for gravity. And so you could worry whether these gravitational symmetries could be anomalous. And in fact, the answer is that they are not anomalous, and it requires some clever constraint among the various charges of the fields in the standard model. And indeed, one can go through and check that the standard model does not lead to a gravitational anomaly, in addition to an anomaly for the gauge theories. So that's another pretty strong constraint. So although the matter content of the standard model and its charge assignments looks sort of random, once you start putting in the constraints of these anomalies, there are actually fewer free parameters than you might expect. So this is not something that really is in the scope of this course. I mean, next year there's a course on the standard model, which you should all take if you're here, where this sort of thing will be discussed in much more detail. But today I wanted to discuss the quark sector. The quark sector actually, in many ways, proceeds very similarly to the lepton sector. There is one important distinction, which is something I wanted to draw attention to, that is related to CP violation in the standard model. But roughly speaking, The quark content is very similar to the lepton content. So we have a doublet of quark fields. So here, I'm never going to write out the color indices explicitly. Color is unbroken, so there's nothing terribly interesting going on there. I might just label it with an index, but I'm not going to write it out explicitly. But if I write out the SU2 doublet explicitly, then this quark doublet will have two components, typically called the up field, the up and down quark fields. And then you have an up bar, an anti-up, and an anti-down. And the up and down transform in the three-dimensional fundamental representation of SU3. The conjugate fields transform the conjugate representations, and they have some U1 charge assignments as indicated here. And as we'll see, when we translate that into their electromagnetic charge assignments, this will translate into the familiar statement that all of the quarks have charge 1/3. So that if you bind 3 of them together, you'll get something with charge 1, such as a proton. Okay, and again, I emphasize that U bar and D bar, the bar is part of the name of the field. Okay? And that as with the leptons, these are left-handed vial spinners. Okay? So it's totally straightforward, given this, to write down the kinetic term. I'll just write it out very quickly. But so the kinetic term for a vial fermion involves a sigma mu. So it's a fermion. So there's one derivative. There's a sigma mu, which is sort of the analog of the gamma matrix for vial spinners. Vial spinners are only 2 components, so you have a 2-dimensional Pauli matrix. And I'm suppressing here the vial spinner index, as I usually do for spinners. So just remember in the back of your head that Q and Q dagger are 2-component row and column vectors, respectively, for that vial spinner index. If I wanted to, I could also write out the gauge theory indices. So for example, I could call alpha an SU3 index, and I an SU2 index. Then you would have an alpha and an I here. And for example, this covariant derivative is exactly what you would expect given its charge assignments. So it couples to the gluons, the SU3 gauge fields, in the usual way. So here, this T3 are the generators of SU3 in the fundamental representation, so otherwise known as the Gelman matrices, which you are hopefully familiar with. And then we have, and so that acts on the color index. And then we have a I there, a similar coupling to the SU2 gauge fields because it's a doublet. So there I've called the index I, so there's a Q alpha J. Okay. So notice that the SU3 gauge fields couple to the SU3 index right here, the SU2 gauge fields couple to the SU2 index right here, and then we have the hypercharge gauge field, so minus I G1 times B mu Q alpha I, and we have to include the value of the hypercharge, which is 1/6. Okay. I suppose I'm using a slightly bad notation where I'm using the same symbol here and here to refer to the SU3 and SU2 gauge fields. And so in just a second, we're going to rewrite this in terms of the W and Z bosons and the electromagnetic gauge field. So hopefully that won't be too confusing. And in fact, the formulas are going to be long and complicated. So when I say we're going to rewrite it, what I really mean is we're going to imagine rewriting it rather than writing out every term explicitly. And then we have similar terms involving the other fields. So for example, you have the up field, the anti-up field, so that we get a sigma bar mu, d mu, u bar, alpha, along with a similar thing for the down quark. Okay? And here I am writing, so my upper alpha index is an SU3 index that is, and sorry, I guess an upper alpha index is referring to an SU3 index telling us that it lives in the 3 bar, and a lower one lives in the 3. And when we contract them together, we get a singlet because the 3 times 3 bar contains a singlet representation. I don't know if you worked that all out in your problem set. Hopefully that's more or less clear. Think about the case of SU2. If you have a 2 and a 2 bar, that's a row vector and a column vector, and together you can form something invariant. Or in SU3, you have a 3-dimensional row vector, which is, I suppose, well, you have a 3-dimensional column vector and a 3-dimensional row vector. Which of those you call the fundamental and which you call the anti-fundamental is, I suppose, a bit of convention. Usually you call the column vector the fundamental, the row vector the anti-fundamental. You take the dot product, i.e. sum over alpha here, and you'll get a scalar quantity, something that doesn't transform under SU3. Okay, good. So this is the kinetic term, including the couplings to the gauge field. And so what other couplings can we write? So now remember, the rule that we use is that we write down every coupling that is consistent with gauge symmetry that is renormalizable, because that's what we expect to be relevant when we study the theory at low energies. So the first thing that you might hope is that you could write down some sort of mass terms for the quarks. Okay. Well, what would they look like? They would look like something bilinear in the quark fields. Okay. So they'd go like q squared with no derivatives. But if you start thinking about it, there's actually nothing that you can write down that is both Lorentz invariant and gauge invariant. Okay. So for example, you could try and write down something like q dagger q. But if you think about it, that's not actually Lorentz invariant. Okay. Why? Well, Q is a Weil spinor. So if you think about its Lorentz transformation properties, remember the Lorentz group can be thought of as 2 copies of SU2 that are related by complex conjugation, and a Weil spinor an SU2 right times an SU2 left. And the statement that you have a left-handed Weil spinor means that it's a doublet under the SU2 left and doesn't transform under SU2 right. Sorry, SU2 left there. Whereas this guy here transforms under SU2 right, because when you do complex conjugation, remember those 2 were generated by J plus IK and J minus IK, where J was the generator of rotations and K was the generator of boosts. So this thing is actually not a scalar. Okay. So you can't construct a scalar this way. Okay. You could construct a scalar if you just have 2 copies of Q. Okay. Because you could have a doublet times a doublet, and you could take one as a row vector, one as a column vector. Or actually, to say that more correctly, you could imagine that you could write something like this. Right? So if you want to get a scalar out of 2 Weil fermions, you can write a scalar quantity like this, where A and B is the fermion index. But then you ask what happens to the gauge theory index. And what happens, well, so the easiest way to see that this is not gauge invariant is to note that these guys both have hypercharge, that's non-zero. So they both have hypercharge 1/6, and 1/6 plus 1/6 is non-zero. Okay, so this is not hypercharge invariant. It also has a color index, 2 3s, which you need to worry about as well. But at the end of the day, you can't write down either of these terms. There's no possible mass terms. However, there are coupling terms describing Yukawa couplings between the Higgs field. So, and I'll try and carefully write out every index here, and the various quark fields. And if you go through the exercise, there are 2 possible Yukawa couplings that one can write down. So if you remember, this is actually different from the case for the lepton sector, where there is only one possible Yukawa coupling you could write down. This actually has interesting implications, as we'll see in a minute. So let me just run through this here. So remember, I and J is the SU2 gauge theory index. I'm not going to write out explicitly the spin 1/2 vial index. Okay, that's just going to be contracted just as it was right here. So you know, this guy and this guy, those are spin 1/2 vial fermions. They're left-handed, so you can crack them using that epsilon tensor. And then, so here you can see we have a 3 index and a 3 bar index, which are contracted together. And we have an SU2 doublet index here and here, which are contracted together. And you can also check the hypercharge assignments. So the Higgs field has hypercharge -1/2. Q has hypercharge 1/6. And D has hypercharge 1/3. They all sum up to 0. So we get something gauge invariant. Similarly for the second term. Okay, this guy now has hypercharge 1/2 rather than -1/2 because we've taken its complex conjugate. We have the Q's, which have hypercharge 1/6. Up bar has hypercharge -2/3. Again, they all sum up to 0. So we have these Yukawa couplings, and we remember that the Higgs has a VEV. So phi is equal to 1/√2 V0 plus some small fluctuations around that describing the Higgs field. And this leads to mass terms when you expand around this vacuum with broken electroweak symmetry. We find that just by plugging in this VEV for phi. And what do you get? Well, from that first term, you get, well, 1/√2, a y prime, and a factor of v times, so remember that so we have this epsilon symbol here, so we pick out the lower component of Q, which was what we called D. So D alpha, D bar alpha. And likewise, from that second term here, we get a 1/√2 y double prime times v times u alpha, u bar alpha. Okay. So these are mass terms for the up and down quark. If, you know, we're sort of more used to dealing with Dirac fermions than Weyl fermions. So if we want to write this in a slightly more familiar language, we can assemble the down D and D bars, Weyl fermions, into a single 4-component Dirac fermion. Okay. And that color index alpha just goes along for the ride. Okay. Now remember, D and D bar are both left-handed Weyl fermions, and so I have to take a dagger of the lower component to turn it into a right-handed Weyl fermion. Remember that in the Weyl basis for the gamma matrices, the projection onto the left-handed sector gives you the upper 2-component part of a Dirac spinner, and the right-handed sector gives you the lower 2-component part. So that's why the lower 2-component part is conjugated. And then similarly, we have a U alpha and a U bar alpha. Okay. Dagger. So then these are Dirac spinners. And the mass term that I've written here is just the usual conventional mass term for a fermion, okay, for a Dirac fermion, okay, plus mu times u bar alpha, u alpha. Okay. And again, that color index just goes along for the ride. Where md, now the mass of the down quark, say, is a function of the Higgs VEV and that Yukawa coupling y prime. And similarly for the mass of the up quark. Okay. Again, we see that it's the Higgs field that's giving the mass to the up and down quarks, just as for the leptons. Is this clear, more or less? I mean, I'm doing essentially exactly the same thing we did for the leptons yesterday, but, you know, it never hurts to see this sort of thing twice, so hopefully maybe it's a little more clear this time. Any questions before I continue? Yes?
The operation of dimensions that are
Yeah, I'm going to do the charge assignments next. But, sorry, the electron. Yeah, but maybe, why don't you ask?
The charges, for example, the hypercharge.
Mhm.
If we here, for example, we have this operator Q, which was the integral over T3x,
Yes.
J0.
Yeah.
Which
Yes, so we also, so actually later on in this class I'll write down the currents as well. Okay, so indeed, you're exactly right. I mean, so there are currents associated with these other gauge bosons. You know, they're roughly of the form psi bar gamma mu psi, just as they were for Dirac fermions. I'll write them all out explicitly. Okay. Before I get there, there's actually one or two I wanted to, yeah, I'll get there in a little bit. Okay. Absolutely right. Good. Good question. Other questions? Okay. So what are the electromagnetic charges here? So remember that the electromagnetic charge, Q, is the thing that's generated by this element of U2, which we could write as, well, I guess we've written it down here. It's sigma 3 plus the identity matrix, so, or T3, I guess we called it, not sigma 3, plus, so the charge, the electromagnetic charge of a field, is given by its T3 eigenvalue plus its hypercharge assignment. That's just the statement that electromagnetic charge, the unbroken part, is generated by that matrix right there. So we can then go ahead and evaluate that. So remembering that T3 was just 1/2 times the Pauli matrix sigma 3. So, for example, T3 on the up quark is 1/2, and T3 on the down quark is -1/2, and but just because those were the upper and lower components of the SU2 doublet, and on the up bar and down bar, these were equal to 0 because those didn't sit inside an SU2 doublet. And so, including the fact that Q bar has a hypercharge assignment of 1/6, you see that an up quark has charge 2/3, and an up bar has charge -2/3, and similarly a down quark has charge -1/3, and a down bar has charge 1/3. Okay. So, so far everything has proceeded very similarly as with the leptons. There's one important difference of the quark sector with the lepton sector, however, which arises when we think about the fact that the standard model actually includes 3 generations of quarks and leptons. That is to say, we have to take 3 copies of everything that we did up above. So the easiest way to do this is to introduce an index, another index. I mean, these fields have lots of indices. So I'll call this capital I. It'll be a generation index. Okay. And then, for example, the kinetic term, say, for the quarks, well, now, that'll just be diagonal in the generations. So, I guess, here, I'll write down the lepton one first. So let's just do the leptons first. So here, this was the lepton kinetic term. Oops, sorry. What am I writing down here? I need a covariant derivative. d mu ij L, J, I, along with a similar term for the electrons. So here I just have a generation index that's going along for the ride. As usual, the repeated indices are summed over. And we have some Yukawa couplings. So we have Yukawa couplings from yesterday. Well, you have a Higgs field in the SU2 doublet that is contracted with the lepton field times the positron field. But now we have now the Yukawa coupling, instead of just being a number, can be a 3 by 3 matrix. Okay. So the Yukawa couplings can be a 3 by 3 matrix. And in particular, because we always add in the Hermitian conjugate here, it can be a 3 by 3 complex matrix. In particular, we've now, we've triplified, if that's a word, the lepton and, the L and the E bar field. And so there's now 9 possible, there's a whole matrix worth of Yukawa couplings that you can write down. This might seem to make life much more complicated, but in fact, it turns out that in the case of the lepton sector, there's nothing particularly terrible you need to worry about. And the reason is that we can always make a change of basis where you multiply the lepton triplet, where now I'm thinking about the triplet, the 3-component column vector in the generation space, by some unitary 3 by 3 matrix. Let's call it L. And similarly for the E bar field, so let's call that matrix E bar. And what happens when you do that? Well, if you choose L and E to be unitary, then the kinetic term that you're writing up here is invariant. Okay. So if you think about that, if you act on this guy with the unitary matrix, and then this guy with a unitary matrix, when you take the adjoint, you get U dagger times U, or I guess I called it L dagger times L. Those things cancel. So you can always do a change of basis. The kinetic term will remain invariant, but this matrix Y will transform by the action of, I guess it's L dagger on the left and E bar on the right. And then it's a result in linear algebra that you can take any 3 by 3 complex matrix, and if you act with a unitary on the left and a unitary on the right, then you can make that diagonalize. You can make that diagonal with real eigenvalues. So what does that mean? That means by making a convenient change of basis, we only have 3 real Yukawa couplings, 1 for each generation. Okay. One that gives the mass to the electron, 1 that gives the mass to the muon, and 1 that gives the mass to the tau. Nothing too complicated going on here. Now what happens if you have the quarks? Well, the kinetic term is very similar. But let's take a look at this Yukawa term. So the Yukawa, so unlike the lepton sector, the quark sector now has 2 different possible Yukawas. So there is the Higgs. I mean, God, you go crazy if you write out all of these indices. And I'm even suppressing the Weil index. So the quark fields really have 4 indices, right? I mean, they've got a generation index, a Weil index, a color index, and an SU2 doublet index. Okay. For a total of what? 2 times 3 times 3 times 2. That's a big number, whatever it is. A total of whatever that big number is, different fields. And then, okay, then we have, and then so we have some 3 by 3 matrix of Yukawa couplings here that I'll call Y prime ij, that generalize that Yukawa coupling Y prime. And then we have a phi dagger I Q alpha I generation index U bar alpha j, and a 3 by 3 matrix of Yukawa couplings Y double prime. Okay. Now, as before, y prime and y double prime are now 3 by 3 complex matrices. The difference with the lepton sector is that if you think about the unitary transformations that you're allowed to make, in particular, if you took q times a unitary times q up to a unitary times up and down to a unitary times down, you now have, how do these guys transform? Well, y prime goes to something like q dagger y prime times u, or I guess it was d, and y double prime goes to q dagger times y double prime times d. Sorry, what am I writing down here? That's a capital D. That's a u. So you now see that what we're trying to do, whereas previously for the leptons we had one 3 by 3 matrix of couplings and two unitary matrices that we could use to make it diagonal, here we have two 3 by 3 matrices of couplings, but we only get 3 unitaries rather than 4. In particular, we have to multiply both of those guys on the left by the same unitary matrix. Okay. So that means that they can't be simultaneously diagonalized. So the coupling sector for the quarks is actually much more complicated than the coupling sector for the leptons. Okay. And in fact, this observation was responsible for the Nobel Prize, I think, was it last year, 2 years ago? Anyway, okay. So the way that people typically write this, so what we could do here is, for example, diagonalize y prime and leave y double prime non-diagonal, or diagonalize y double prime and leave y prime non-diagonal. But in fact, the typical choice that is made is actually to do neither. Okay. Instead, what we would like to do is consider a more general set of transformations which diagonalize both y prime and y double prime, but now make the kinetic terms non-diagonal. Okay. In particular, what we want to do is instead take your quark field. Sorry, I guess I should have put my bars in here. I was not very religious about my bars. Okay, good. I take my quark field and I write it as an up and a down. And I want to transform the up and the downs separately. When you do that, so what is the Yukawa coupling? When you write it out explicitly in terms of the ups and the downs, well, this is basically what we wrote down earlier. You know, so we had a phi, or I guess it would be a v plus h in unitary gauge. We have a d alpha I times a d bar alpha j times a y prime ij. And the second term, writing it out explicitly in this, writing out this explicitly in this SU2 basis, we get 1 over root 2 v plus h times u alpha I, u bar, alpha j, times y double prime, ij. And now, if you allow yourself to make separate complex charge rotations, complex rotations of the ups and the downs, along with making those rotations on the up bars and the down bars, then you can make all of the Yukawa couplings diagonal. Okay. So you can make the Yukawas diagonal. But you do so at the price of making the kinetic term non-diagonal. In particular, because we're now treating the two components of that SU2 doublet differently, you're going to make the coupling to the SU2 gauge bosons non-diagonal. Okay? So when you actually write down the coupling between some of the electroweak bosons, the W bosons in fact, to the up and down quarks, you find that there's some mixing term between the different generations. Is this more or less clear? I'd like to write this out a little bit more explicitly, but maybe before I do so, I can pause and see if there are any questions. I realize that you're sort of being drowned in a sea of indices here. I mean, you know, the temptation is to sort of use some sort of index-free notation where all of the indices are suppressed. But then it's very easy to get misled and to actually not understand what's going on in full detail. And so I think at least once everyone should do the exercise of writing all of this out in terms of all of its indices. Okay. Good. So explicitly, what do these generation mixing terms look like? So explicitly, if we think now about the kinetic term for the quarks, so you have a bunch of terms that are diagonal, but the terms that are off diagonal are going to be the ones that couple the W boson, couple to the W bosons. So I guess we could call those J mu plus and J mu minus. So as usual, conventionally, we call the thing that's linear in W mu in the action the current J mu that couples to W mu. So now, if we were just dealing with, for a standard Dirac fermion, remember that J mu is just psi bar gamma mu psi. So for a single generation of quarks, what is the current, say, that couples to W plus? Well, that should take the form psi bar gamma mu psi. But remember that W mu plus was the generator that multiplied that component up there, okay, in terms of the 2x2 unitary matrix representation of the electroweak sector. And so that is going to mix an up and a down, okay? So in terms of the fermion, the Dirac fermion notation, we could write that as, so if this is our four-component Dirac fermion, so you'd write it as d bar gamma mu u. And for three generations, so this the current that couples to the W bosons involves one up quark and one down quark. And the current that couples to the three generations, so now this guy is going to be non-diagonal, okay, because we've made the two different unitary transformation matrices on the first and second component of the quark doublet. And so you get d, excuse me, sorry about that. You get a d, you get a generation index, and you'll get some matrix, Vij, times Uj. Okay. So V is some 3x3 complex matrix. So if you wanted to write it out explicitly, so in particular, in terms of these matrices that we wrote down above, okay, what I've done is I've acted separate. I multiplied the U's by some 3x3 matrix capital U, the V's by some 3x3 matrix capital V, and so this is going to be U dagger times D. Okay. And this is known as the CKM matrix. For Kabibo, Kobayashi, and Masakawa. Two of whom I think won the Nobel Prize last year. Is that right? I think that's right. Or did all three of them win it? I don't actually remember. There was something controversial about this, but I don't actually remember what it was. But what is the important point here? The important point here is that this matrix describes couplings between the different generations of quarks. And in particular, V is a 3x3 complex matrix. And so if you work out what the currents are, so J mu plus is going to be something like d bar, v dagger, sorry, there's a gamma mu here, of course, v dagger, gamma mu, u, and J mu minus is something like u bar, v, gamma mu, d, then the fact that V is complex means that the currents J mu plus and J mu minus are not real. And if you think about it, this tells us that the standard model is CP violating. Why? Well, remember that these are the currents that couple to W plus and W minus. W plus and W minus have opposite charge, and, or maybe the best way of saying that is that your theory is always T invariant, and time reversal involves complex conjugation because it's an anti-unitary operator. So the statement that these currents are complex is the statement that the theory is not time reversal invariant. Or that the statement is CP violating. So the presence of 3 generations and the fact that there are these 2 different kinds of Yukawa couplings that you can have for the quarks means that the standard reversal is not time. The standard model is not time reversal invariant. Okay? There are processes that, there are scattering processes where you can run them forwards in time and run them backwards in time, and you won't get the same answer. So it's, so we've already seen that the standard model is not chiral, so it's not parity invariant, and now we see it's not time reversal invariant. It's only, in fact, under the combination C, P, and T that the standard model is invariant. In fact, there's a kind of deep and sort of famous result in quantum field theory that any unitary theory needs to be CPT invariant under both charge conjugation, parity, and time reversal simultaneously as a consequence of Lorentz invariance. But it need not be invariant under any one of those symmetries individually. Okay? And indeed, it turns out that the standard model takes advantage of that fact and is only invariant under those 3 symmetries simultaneously. Okay. Of course, the CP violation in the standard model is small because it involves mixing between the generations. And so, it's certainly something that is observed, but it is a relatively small effect. Okay, are there any questions here? I realize that, to some extent, the writing down of the standard model is the culmination of everything we've been working for in this class. But on the other hand, the standard model is just some very, very complicated quantum field theory, and so it's a little hard to wrap your heads around all at once. What I thought I could do for the rest of class today is talk about some of the computations you could do using some of the ingredients that I've given you. So I'll talk a little bit about various interactions between fermions and maybe about neutrino masses. But before I do so, let me pause and see if there are any questions. Yes?
So if quarks participate on the interaction like proton and neutron don't, or they just cancel out? Protons and neutrons do. Let's see. These objects do participate in weak interactions, but
the weak interactions are very weak. Okay. So as we'll, so actually the next thing that I wanted to do is to describe some of the scattering processes that we can study for weak interactions. Indeed, quarks and quarks do participate in these. Although they're most easily measured in terms of leptons, but quarks do participate. Any questions? I mean, to some extent, in order to understand the standard model, it's to some extent an exercise in bookkeeping. There's a lot of different moving parts to keep track of. But the structure is really nothing more complicated than any other quantum field theory we studied this semester. But I am not, for example, going to write out the Feynman rules for the standard model. Okay. I mean, we could, but it's just going to be, there's lots of terms, okay, and lots of indices. So I'm not going to do that explicitly, but you do have all of the ingredients in order to do so. Any questions? So I thought I might just take the next little bit to talk about a few simple processes that one can compute in the standard model. So let's consider the coupling of the various matter fields in the standard model to gauge bosons. So, for example, you'll have a coupling of the electromagnetic field to an electromagnetic current. Okay. That electromagnetic current, I've told you what the charge assignments, the electromagnetic charge assignments of the various fields in the standard model are. So you could then, it's a straightforward exercise to go ahead and write down that current, and then you could start computing just as we did when we studied electromagnetism in QED. You could start computing corrections to anomalous magnetic moments and stuff like that, just as we did when we were studying QED. So I thought instead it would be more interesting to study something new that's not present in QED, which would be the coupling to one of the massive gauge bosons, say the W boson. So the current that couples to the W gauge boson, so remember, say W plus is the thing that's proportional to the 0, 1, 0, 0 component of the unitary matrix. So that's something that will couple an electron to a neutrino. So if we assemble our electrons, our two-component Weyl spinners describing the electron and the positron, into a single Dirac spinner, and then the neutrinos, well, the neutrino can be assembled into a sort of simple four-component Dirac spinner whose second component is 0 because there's no antineutrino yet. Okay. That'll come. And then there'll be a similar term involving the down and the up quarks. And we could go ahead and compute scattering using the standard Feynman rules. But if we're interested in processes, say where you have, say, scattering of an electron off of a neutrino, where the momentum scale is much less than the mass of the weak boson, of the W boson. So in particular, we're interested in studying a process like this. So here, say we would have an electron and a neutrino scattering via some W boson to an electron. Oops, I drew my charge arrows wrong there. An electron and a neutrino. Then you might be interested in computing this process. Now, that Feynman diagram might look awfully funny for a second because we're used to these arrows describing the fermions, keeping track of the U1 charge, of the electromagnetic charge. But remember that, and you know, a neutrino has no charge, and an electron has a charge. So if we were studying QED, you couldn't write down a diagram like this, okay? You couldn't write down a diagram where a charged particle and an uncharged particle give you a photon. But remember that the W boson carries charge, okay? That's why we put a plus. The W plus carries charge. Or I guess it would be a W minus in this case. Sorry. If we studied electrons instead of positrons. So this is a process where an electron and a neutrino would scatter off of each other via the exchange of a W boson. And in fact, well, we could go ahead and write that out explicitly. It's not terribly difficult. But in fact, there's a neat trick that you can use to think about this if you're studying it at momenta that are much less than the mass of the weak boson. So essentially what we can do is integrate out the W boson. So what do I mean by that? Well, remember that the interactions of the various fields with the W boson are, in the Pythagorean language, described by an integral over W, the W boson field, of a kinetic term plus an interaction term plus a mass term for the W and if you think about it, when you study the scattering processes that happen at momenta that are very small compared to the W boson mass, what does that mean? That means that you can neglect this term here. Okay. You can just set it equal to 0. So now you're thinking about an integral with no derivatives in it. So this is just a normal Gaussian integral. And you can do it by completing the squares. Okay. And what do you get? Well, you get some overall number, which is something that we don't care about, times the exponential of j mu, with a coefficient that's g2 squared over the mass of the W boson. So what am I doing when I say this? What I'm doing is I'm saying that we can take this W boson exchange and, in the true standard model, this is, a process that we think of via the exchange of some internal particle. But when you're studying it at momenta much less than the mass of that particle, you can just approximate it by a 4-point vertex. So here we have the electron on top and a neutrino on the bottom. Sorry, I can't get my arrows right. And so from the point of view of the low energy effective quantum field theory, we can ignore this W boson and just regard the theory of the electrons and neutrinos as having an additional 4-point interaction. And the strength of this interaction, so a 4 Fermi interaction is called it's called a Fermi interaction, okay? And its coupling is called the Fermi coupling, G. And the strength of that coupling is going to be G2 squared over the mass of the W squared. So intuitively, this hopefully makes sense. If the W boson is really, really massive, then this is going to be a very small coupling between these guys. Okay? It's going to be very difficult for them to exchange W boson. But if you increase G2, which is the strength of the coupling to the W boson, then this interaction strength is going to increase. Okay? You know, one thing that's sort of cute about this is that from the point of view of the low energy effective field theory, when we've integrated out the W boson, this 4 Fermi interaction term, the J mu, looks non-normalizable. So the 4 Fermi interaction looks non-normalizable. So what's going on here? Well, what's going on is that at high energies, at energies of order the mass of the W boson, everything's nice and normalizable. But if you look at the low energy field theory and you integrate out, that is to say, you look at the effective theory that comes from after you integrate out the W boson, the 4 Fermi interaction is non-normalizable. That means it's negligible at low energies, right? And so all that means is that this process, well, it's going to be very hard to see at low energies. I mean, that makes perfect sense. At energies far below the mass of the W boson, it's going to be very difficult to measure the exchange of a W boson. So in fact, this is called a Fermi coupling because Fermi wrote it down, right? That's usually how these things work. Well, it's occasionally how these things work. Indeed, one of the things that puzzled people when Fermi wrote these sorts of interactions down is that they were non-normalizable. And so Fermi's theory of interacting fermions, electrons, neutrinos, and so forth was regarded as a failure because it was discovered to be non-normalizable. But at the end of the day, I think sort of post-Wilson, people realized that this really isn't a problem per se. It just means that this non-normalizable theory arose from ignoring degrees of freedom that you could ignore, okay? Namely degrees of freedom that are relevant at higher energies than the ones that Fermi was interested in when he wrote down his theory. Let me say that perhaps a little bit more clearly. If you studied the theory of interacting electrons and neutrinos at very low energy, and then you start trying to increase the energy, you'll see 4-point couplings like this. But then at some point, at sufficiently high energy, say when you're studying the interchange of momenta that are of order the weak boson mass, suddenly you'll discover that there's some substructure to this 4-point interaction, and that you should really be more properly replacing it by some exchange of W boson. And this is how effective quantum field theory works. At very low energies, you study it only in terms of the normalizable couplings. As you increase the energies, you have to start taking into account the non-normalizable couplings. And presumably, typically, it's replaced by something more fundamental at high energies. Okay. The only exceptions would be theories, say asymptotically free theories, where as you go up to high energies, all the couplings turn off, and you get non-interacting theories. Okay. I just have a few minutes left, so maybe I'll make one more comment. So the theory that I've presented to you up above is known as the standard model of particle physics. Okay. It's wrong in a very, very obvious way. Okay. So in the standard model of particle physics, the neutrinos were massless. And if you read a textbook in quantum field theory, they'll talk about the new standard model and how the neutrinos are massless. But if you've ever been to a physics colloquium in the last several years, in the last 5 to 10 years, you've probably learned that neutrinos are actually massive. Okay, so one actually has to modify the standard model to account for this. And it turns out that this is a very, very simple modification to the standard model. So to take this into account, what do we need to do? So does anyone know what do we need to do? Given what we've seen so far. Okay. So the quarks, both the up and the down, were massive, but for the leptons, the electron and neutrino, one was massive and one was massless. Okay. So can anyone tell me what we need to do to the quark, to the lepton sector in order to allow the neutrinos to have a mass? Anyone? Let's see if people have been paying attention. Well, it's not that there's a symmetry that we need to break. Let's investigate here. Okay, let's do some investigation. Okay, so what's different about the lepton sector versus the quark sector? Forget about the color index. That doesn't have anything to do. Remember, masses came from electroweak symmetry breaking. What's different about the electroweak sector of the quarks as opposed to the leptons? Well, what's different is that on the quark sector, we had this doublet here and of left-handed vial spinners, and each of them had a friend, okay? Each of them had an antiparticle. Whereas for the lepton sector, you have this doublet here, but only one of them has a friend. So if you want the neutrino to have mass, he needs a friend to play with, okay? The left-handed neutrino needs an antineutrino. A massless field can be its own antiparticle, a uncharged field can be its own antiparticle, but for a massive charged field, you need a new field to be its antiparticle. So in particular, we need a new field, let's call it nu bar, an antineutrino field, neutrino, to couple to the neutrino. And indeed, I think it's a reasonably straightforward exercise. Ooh, maybe I'll give this to you on your problem set. Oh, that'll be exciting. It's a good thing I didn't finish writing it yet. So in particular, if you have an antineutrino field, and what charge assignments should we give it? Well, all you need to do is make it uncharged under every gauge group. Okay, so it doesn't couple to any of the gauge fields. Then it'll have a kinetic term, so it's a left-handed vial spinner. Then you'll be able to write down another set of kinetic terms in the lepton sector, okay, where you have another Yukawa coupling, so phi dagger I, an Li, and a antineutrino. And then this will give a mass term to the neutrinos. So, in a sense, the fact that neutrinos have masses just means that the quark and the lepton sectors are more similar than one originally thought. Indeed, long before neutrino masses were discovered, it was postulated that neutrinos had mass and that there'd be an additional antineutrino field that one had to include in order to account for this. And in fact, in grand unification models based on SO10 as opposed to SU5, those only work if you include an antineutrino field that accounts for the neutrino mass. Okay. So to some extent, the observation of neutrino mass might be some sort of just additional little tiny bit of evidence for an SO10 unification versus SU5 unification, which is good because SU5 unification has been ruled out experimentally, okay? Or at least the most simple models of SU5 grand unification lead to proton decay, which has never been observed. whereas SO10 unification does not. So if I had to bet, I would bet that all of the gauge fields unify into SO10 rather than SU5, despite the problem set that's due tomorrow. There's one slight mystery remaining, okay, regarding these neutrino masses. And people make a very big deal about it, but I don't actually think it's that big a deal. Which is that the neutrino, the reason why neutrinos were originally thought to be massless is that this mass actually, so let's write this out explicitly. So in terms of the mass term, so this gives you some mass term, y tilde times the Higgs vev times nu bar, okay, plus Hermitian conjugate. So this gives you a mass term. Let's call it m tilde. And if this were the only mass term that you got, then you would have a little bit of a puzzle as to why neutrinos are so light. So the neutrino masses are around an electron volt, whereas the electron mass is around 1 million times that. It's 0.5 MeV. So you have a little bit of a mystery. So in particular, what this would mean is that the Yukawa coupling y tilde here that describes the coupling that gives you the neutrino mass has to be 6 orders of magnitude smaller than the Yukawa coupling for the electrons. And whenever you have couplings that are either incredibly large or incredibly small, that seems unnatural. Typically you would expect, in the absence of some symmetry or some, slightly weakly broken symmetry to explain why a coupling is very small, you expect couplings to all be of order 1. So people sort of make a big deal out of the fact that if you just naively include this term, this coupling is, has to be of order 10 to the minus 6, as opposed to order 1. In fact, there's a very natural mechanism to explain this, which is known as the seesaw mechanism. In order to understand the seesaw mechanism, let's just remember the rule that we always abide by, and the rule is that you add all terms in the Lagrangian that are renormalizable and consistent with your symmetries. Okay? And indeed, if you think about it, the antineutrino had no gauge field assignments whatsoever, carried no charge under gauge symmetry. So unlike all of the other particles we had, where we couldn't add an explicit mass term for them because that would violate the gauge invariance, for the antineutrino, you can just write down a mass term. Okay? So you could just write down a mass term. There it is. Okay? Maybe you want to add the Hermitian conjugate. And then, if you look at so this is the mass for the nu bar field. If you look at the total set of mass terms in the standard model, including the explicit term for the antineutrino, as well as the term that came from electroweak symmetry breaking, what do you get? Well, if you write out everything in a 2-component basis, you get something like this. So that's what the mass terms look like. Right? All I've done here is take this term here and add it to this term and write it out in a 2-component basis. The 0 here, this is the 0 that comes from the fact that we originally didn't have a mass term for the neutrinos. This is the new term that we get if we add the antineutrino, which can now couple to the neutrino with a mass term. And this is the term that arises if we remember that the antineutrino itself can have a mass term, okay, because it now doesn't have gauge charge. And so the thing to notice about this is a 2-by-2 matrix. And if we assume that M is much bigger than M tilde, then this 2 by 2 matrix can be diagonalized and it has eigenvalues. So one of the eigenvalues is, of course, just of order capital M, okay, because M tilde is very, very small. And the other eigenvalue is M tilde squared divided by capital M. So what does this mean? This means that if we take the Yukawa coupling Y tilde to be of the same order of magnitude as the Yukawa coupling for the electron, so that the M tilde we wrote down above is of order 1 MeV. And then if we take M to be about 10 to the 3 GeV, then that means that M tilde squared over M is about an electron volt. Okay. So this is called the seesaw mechanism. It's called the seesaw mechanism because the idea is that you have this intermediate mass scale M tilde, but if you add in a very heavy mass, then the actual eigenstate of the mass matrix has a very light mass. So the very heavy mass cancels out the very light mass to give you this intermediate scale. So in a sense, this can be used to explain the small masses of the neutrinos. It just means that there's some new particle out there, an antineutrino, which we haven't seen yet. And there's two reasons why we haven't seen it. Well, it doesn't carry any charges, so it's hard to get it to interact with things. And it's very heavy. Okay. And presumably, if we built an accelerator that was sensitive enough to probe at those energy scales with enough accuracy, we would see the antineutrino. So I don't think it's a particular mystery why the neutrinos are light. That said, it does mean that there is something very interesting happening at this scale, at the TeV scale. And so I think, so I think that maybe is where I'll leave our discussion of neutrino masses. I mean, maybe I can just end with a bit of philosophizing. Okay. So we spent the last week thinking about the standard model. So once you include the standard model, the neutrino masses, the standard model has, I think, 20, I wrote it down earlier, I think it has 26 undetermined free parameters. Okay. We have the various lepton masses, so there are 6 leptons, so we have 6 lepton masses, 6 quark masses, let's see, a bunch of angles in the CKM matrix, okay, that describe the couplings between the generations. It turns out that once you exploit all of the remaining freedom that you have left to redefine the fields, you have 4 degrees of freedom left over. So you have 4 in the quark sector, 4 in the lepton sector. What does that give you? Let's see, 8 plus 6 plus 6, whatever that is, that's 20. Then we have 3 gauge couplings, that brings us up to 23. Did I miss some? Oh yeah, we got theta QCD. I think we mentioned theta terms in the discussion of electromagnetism. So you can have a coupling of the form F mu nu, F rho sigma, epsilon mu nu, rho sigma. Turns out you can only have such a coupling for the SU3 gauge field, not for the SU2 times SU1. That's related to the fact that it's only the SU3 gauge theory that has non-chiral matter. And then you have 2 more parameters related to the Higgs field. Okay, you have lambda and the Higgs valve, or the Higgs mass and the Higgs valve. Okay, 26 undetermined parameters. Where do they come from? How do we derive them? I mean, there are various models that people try and use. At the end of the day, presumably it's the case that the standard model is just another low energy effective field theory that's going to be replaced by something else. You know, if you go up another few orders of magnitude, you'll discover that what we previously thought were fundamental particles might be bound states of other more fundamental particles. That's one possibility. You know, another possibility is that the standard model is correct all the way up to the Planck scale. You know, something has to happen at the Planck scale. At the Planck scale, there's gravity, which is the thing that we have totally avoided in this course. At the Planck scale, we're going to need to quantize gravity. And I think one of the deep and unanswered questions is whether there is anything in between here and there. Okay? If there's no other new dynamics that appears between the standard model scale and the Planck scale, then presumably we would have to understand quantum gravity in order to understand the values of the couplings in the standard model. But maybe there's some other principle at work. You know, I mean, I think my personal preference is for some grand unified theory that would happen before the Planck scale. But I think it's an open question. Okay, so that's all I wanted to say. Are there any questions before I finish?
Yeah,
Yes.
Like electroweak couplings and like all these G's floating around.
The 3 gauge couplings.
Yeah. We look at the Landau pools.
Yeah, good. Okay, so we discussed this very briefly. This is a great question. When I talked about asymptotic freedom. Okay. So let's graph 1 over the coupling squared, okay, which is known, oh, sorry. Yeah, let's graph 1 over the coupling squared. Okay, which is otherwise known as alpha inverse, because those are the things that run linearly with energy scale. So it turns out, so electromagnetism, so U1, okay, I guess now I can be honest, last time I drew this chart, I called the U1 electromagnetism. I was sort of lying. It actually has to be hypercharged once you get above a certain energy scale. But there's a U1 coupling which has a Landau pole, which means that it runs strong. So 1 over g squared decreases as you go up in energy. So this is supposed to be energy scale. Okay. And this is supposed to be a logarithmic scale. Okay, so here is us, say, down at the GeV scale if we're lucky. And then, so the U1 runs strong. Okay, it has a Landau pole, as we learned. But the G3 and G2 both run weak. Okay. And they all seem to come together at an energy scale referred to as the gut scale that is around the Planck scale. It's a couple orders of magnitude below the Planck scale. Now, whether these couplings exactly unify or not really depends on what's happening in between here. Okay. So, you know, people who study particle physics beyond the standard model sometimes refer to the postulate that there are no new degrees of freedom between here and the gut scale or the Planck scale as the statement that there's a desert. Okay? So people often say that, you know, if there's a desert, so nothing for the next 16 orders of magnitude, then these gauge couplings more or less unify. Okay? One of the theories that people really like to think about is called supersymmetry. In supersymmetry, it turns out that that makes the gauge couplings exactly unify. Just how impressive this is really is a matter of debate. Okay, like if you read Peskin and Schroeder, he makes it sound like the gauge coupling unification in supersymmetry is incredibly impressive, and if you actually go through, if you actually look at it in detail, it's sort of up for debate how impressive it is. I mean, supersymmetry also predicts that the Higgs mass is less than 9d GeV, okay? Because in supersymmetry, there's a relationship between the Higgs mass and the mass of the W and Z bosons. And so that's wrong, okay? And so there's various things that people try and do to get around this. They say, well, there are these other terms, and you have to do a little bit of fine-tuning and add some loop effects, and you can kind of push it up pretty far, but a Higgs mass of 125 is sort of uncomfortable for supersymmetry. So all of this is to say that we really don't know what happens at higher energies. Yeah. So, for example, it may well be that there's some intermediate scale here where some new dynamics comes in which, say, might change the slope of one of these curves that make them all unified. You know, there are some models that say, well, you know, I mean, one of the interesting possibilities is that, you know, what if, you know, one thing that people like to talk about, so let's say, okay, sorry. You know, so let's say that everything here looks like it's going to unify at some very high scale. Okay. Right. Sorry, I'm not drawing this very well. Okay. I mean, so right now everything looks like it's going to unify at some very high scale. Okay, so that these will all converge right around here. But one of the models that some models that people like to think about are ones where there's some other dynamics here that makes them all unify instantly, basically. You know, it focuses all of these onto a point. So that would mean that the gut scale is actually right around the corner, if that happens. But nobody actually knows if that's right. I mean, there's some other. That's a very interesting thing to speculate because if the gut scale is really around the corner because of some dynamics like that, we could see it at the LHC. So, you know, people like to think about models that might have interesting experimental consequences, and so that's why those things are sort of popular. But at the end of the day, we just don't know. Good. Any other questions? Last chance. Just add another copy of the standard model. So the standard model content, the matter content of the standard model makes the couplings have a particular slope, okay? Just add another copy of it, okay? And then you'll double the slope. Okay? Add 10 copies and you'll make the slopes multiply by a factor of 10. That's pretty stupid. But, you know, it could be right, okay? And it was a model that was come up by that was thought up by very smart people, so I probably shouldn't say that. But no, I mean it's an interesting thing to think about. Yeah. Yeah. Good. Other questions? Okay. So I will send out a problem set tonight.